Hi everyone, thank you for coming. We'll start on top of the hour, so in around 7 minutes. And feel free to check out the PowerPoint and also the paper that I shared in the chat. And we will start soon. Thank you. Hi Z, hi Pravin, hi Wise, Amelia S. Thank you for coming. As I just said, welcome. um, We will start on top of the hour, and in the chat, there's a link for the open source paper, and on top is the PowerPoint presentation that our guest speaker will present today. And yeah, feel free to share the room, and we will start soon. And thanks for coming, everyone. It's the last room of this year. And we will be having the room in the next year, the first one again in on January 5th. So I hope I said your name right. Please let me know how to say your name right. How are you? Can you hear me?
Hi, good morning. Good morning. Actually, good evening, Katerina. This is Weijian speaking.
Yep. Thanks for coming. Welcome. And yeah, good morning to you. I hope you're having a great
Yeah,
start of the
yeah.
day.
Actually, sorry, it's good evening. Yeah, right now I'm in California, so yeah.
And this is the last room of this year that we will be having. So we have the
Okay, great.
honor to.
Thank you.
I are you doing something? Like, are you taking a little bit off during this holiday
Yeah,
season?
we will. Yeah,
Wonderful.
yeah. To get some refresh and also get some more energy for the upcoming year.
Exactly.
Yeah, yeah,
That's
yeah.
nice to hear.
Mm,
I'm glad.
Thank you. Yeah, and I hope you as well, right?
Yes, yes,
Yeah.
I'm also taking off starting Thursday
Thursday. Yeah, yeah.
and then until,
That's nice. Yeah.
beginning of January.
That's right. Yeah.
We we wanted to go back home to Europe, but then my parents came and I
Oh,
don't know,
okay.
a lot of
I see.
people are sick again. So
Yeah, sorry to hear that. Yeah, but hopefully they will get recover soon. Yeah, yeah.
yeah, we're going to visit friends here in the US and
Hmm.
long family friends, and it will be nice
Yeah,
to
yeah.
keep it. And how has your year been like after COVID? Very busy or was
Yeah,
it
right now
good?
everything is all back to normal, more or less, I think. Yeah, so it's in person, everything. We start to be in person actually last fall, so 1 year ago. 2021 October, we start to be in person in the campus. And then we briefly went to remote for about 2 weeks, I think, in January when the Delta variant spike, I think, at that moment. Then afterwards, it's all back to normal, and I think now everything seems to be fine. I think, yeah.
Yeah, everything seems to be fine.
But we do learn quite a bit from the remote instructions. So right now, some of our classes can be done remotely, and some of the meeting can also be done remotely right now. Though most of them is still in person. I think each of them have their own benefits. I think so. Yeah.
Yeah, I agree.
Yeah.
Uh, Was it? Yeah, I agree, but everything has upside and downsides.
Yeah. Yeah.
We have like I have a bunch of meetings that I still do remote, and then other meetings
Mm-hmm.
or in person. It depends, I guess.
Yeah. Yeah. It depends.
Yeah.
Yeah. Yeah. Yeah.
I'm just glad
And
the kids
yeah.
are back in school.
Sorry.
I'm glad the kids are back in school.
Ah. Yeah.
Well,
Yes. That's right. That's right. That's important.
yeah.
Yeah.
Well,
Yeah.
it had upsides too, but I think for the kids it's important to have like a social life and
Yeah. 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 I think totally remote definitely cannot replace the in-person social activity, particularly for kids. Probably. I think. Yeah.
yeah, I mean, the good thing was they could be remote from anywhere. So in the beginning we stayed
Mm.
home, of course, but then they here in New York City, their school stayed closed for 2 years basically
Wow.
remote. So
I see.
a
I
lot
see.
of things started opening up. So we and you know we traveled then, which
Yeah.
was nice.
Yeah.
So and it was we could go somewhere when it was cheaper, right? Now
Mm-hmm.
it's crazy expensive to go during the times again when the
Yeah.
schools
Yeah.
are closed.
That's right.
That's the
Yeah.
downside of it.
Mm-hmm.
But other than that, I think it's better.
Yeah.
I think we can start. And hi, Serena. How are you today? Thanks for coming.
Hello. A little bit under the weather.
Oh no, you're sick too.
Yeah,
Everyone is sick right now.
everyone. I think it's just a cold, but I had a test done earlier in case it's COVID, but I think it's just a good old fashioned cold.
Uh-huh.
God.
Yeah. Sorry to hear that. Yeah. Hope you could recover soon.
Yeah, it
Yeah.
seems to be progressing fast, so
Mm.
be fine.
Yeah.
Okay. I'm glad you still came.
Hmm.
So,
I'm sort of been in bed all day.
okay, so you rested just to be here. That's what.
Right.
Well, welcome everyone to Science Society, and of course, a special welcome to you, Dr. Young. And
Thank you.
before we start, let me give the audience a short introduction so they get to know you a little bit.
Mm-hmm.
And Dr. Weijian Yang is Associate Professor at the Department of Electrical and Computer Engineering um, at the University of California, Davis. And he did his Bachelor in Science at the Peking University in Beijing and his PhD at the University of California, Berkeley. And Professor Young joined the faculty of the University of California, Davis, at the Department of Electrical and Computer Engineering in 2017. And he his research interest lies at the intersection of electrical engineering, biomedical engineering, and neuroscience, which I think is a really interesting one. And he's specifically interested in optical microscopy, biophotonics, integrated optics, and optoelectronics, and neuroengineering. And he's using advanced technologies to study the functional organization and plasticity of neuronal circuits. And he published more than 80 papers, and he is also the recipient of the Career Awards at the Scientific Interface from Burroughs Wellcome Fund and the NSF Early Career Awards. And It's really an honor having you here, especially that you have this really broad, kind of interdisciplinary approach that I think
Mhm.
is really interesting. And usually, before we start with the talk, we ask a couple of interview questions. And our first question is, when did you found out, or did somebody else found out for you? Our last guest speaker said, my parents wanted me to do this, but then I enjoyed it. Like that you wanted to become a scientist and follow this path of
Uh-huh.
research.
Oh yeah.
Thank you.
Yeah. First of all, thank you, Katerina, for the invitation to this Science Society on Clubhouse presentation. It's an honor to be here to share our latest research with you. So now to get back to these questions, I think so. When I was actually when I was a student in the high school, I get interested in science, particularly physics and biology at that moment. Then when I go to college, my original intention is really to go to the biology and physics departments to learn about those subjects. But then, unfortunately, my score at that moment is not high enough. So I end up in engineering, in electrical engineering, but it actually is a very good subject actually, because it's first of all in electrical engineering, it's uh, kind of interdisciplinary already, I would say, because it touch different area, particular both physics and engineering as well. So, and then I continue with my PhD in also in electrical and computer engineering at UC Berkeley. And then after that, then I think I have a little bit more freedom, so that I would like to explore back of my interest, which is biology at that moment. Then that's the result that I go for a postdoc position actually in Columbia University at New York to pursue some interdisciplinary research between electrical engineering and neuroscience. And from there, I pick up the knowledge about like optical imaging and particularly for biomedical application, and also some knowledge of neuroscience. And then afterwards, that I become an independent faculty members at UC Davis, and then this allowed me to continue my research, mainly on optical imaging, optical microscopy, and also some nanostructure, nanophotonics, and then most of these serve as like some of the tools, and then we apply these tools for neuroscience studies. So this is kind of my journey so far to science and engineering. Yeah, yeah.
Wow,
Mhm.
that's really
Yeah,
interesting. And yeah, that's
yeah.
that's wonderful that you maybe it was really good that you first you were kind of forced to do engineering first and then to biology because that's why we talk now. So I'm
Yeah.
really glad. But I
Uh-huh.
I realized that most things that are really important we really don't decide. We think like very important decisions that we make are
Mhm.
important for life, but then tiny decisions or other
Yeah, yeah.
are actually the important ones.
Certainly. Yeah. Mhm.
And is there an interesting story to this, specific project we are talking about? Was it, sometimes there's like a backstory, was very easy to get funding,
Mhm,
maybe
mhm.
really hard,
Yeah,
or
yeah.
yeah.
So for this work is about 3D imaging for kind of photography application, I would say. So, but as I mentioned earlier, actually, my original intentions for our lab is mainly for biomedical applications. So when I start to join UC Davis, um, I wrote a grant about optical microscopy for neuroscience application, which we will talk about that towards the end of this talk today. And the main principle there is to develop something that is thin and compact, so that the rodent, for example, the mouse, the mouse can wear that kind of tiny camera on top of his or her scalp, and then during the mouse movement, without any movement constraint, that we can do the imaging of the brain activity of this rodent. So this is the grant, the proposal that I wrote, and then it was fortunately, very luckily, we got funded, and that is how we start the 3D microscopy, like something called lensless microscopy for biomedical application. And there, our main motivation is to make this device very thin, so that the mouse can wear that while the mouse can still freely behave, right? So we worked for this project for about 2 to 3 years, and I think we got very reasonable result. And then after that, so after this project finished, and then I was thinking that the same principle can actually also be applied for photography application. So instead of doing microscopy, we can also use a similar principle to do the photography, so which is microscopic object. So as a result, we kind of detour a little bit on that, and then I use part of my funding from my startup actually to continue this work, and that is how we come to this project for kind of 3D imaging for microscopic object, which could be cool for maybe 3D vision, maybe for robotic applications, those kind of things. Yeah. So this is how it works. It's actually like kind of like a detour from the biomedical applications. Yeah. But towards the end of this talk, I will show the result from the original project for the biomedical application. Yeah. Mm-hmm.
Thank you so much. Yeah, it's so interesting how it started with this application and then it got really wider and broader, and that's really
Yeah.
interesting.
Mm-hmm.
So
Thank
thank
you.
you for sharing that story with us.
Yeah. Mm-hmm.
And for everyone, the PowerPoint or the PDFs, like the presentation slides, are pinned on top of the room, so please access them. And the stage is yours. Thank you.
Thank you very much, Katerina. So this is actually my first time to do the Clubhouse presentation. So please bear with me if I talk a little bit like maybe too short or too long or maybe too much detail or not. So please let me know. Nonetheless, I will get started. So I have my presentation in front of me, and I hope that I could use most of my words without you going to like with the presentation. But maybe sometimes I will need the assistance from the slide. So I will like indicate which slides and which figure or which item I'm talking about while I go through my talk. So so this talk is about the 3D imaging. So by definition, 3D imaging means that we will be able to perceive not only the like natural X, Y dimension of 2D information, but we will also be able to perceive the depth of the object scenes. So we call that the object scene. So now let's take a look at slide number 2 there. So I would like to start this topic by examining our own eye. So we as a human being, we have two eyes, left and right. So and we know we will be able to perceive the depth. So the main reason that we can perceive the depth is actually due to the fact that we have two different eyes, and these two different eyes they are located differently, right, separating to left and right. So as we saw on these slides, that each eye actually perceive the image slightly different. I mean, they perceive the object seen slightly different. So the left and right, they will, each of them will get an individual image from the object scene. And then based on the difference between these two object scenes, our brain will be able to process the information, and thus we will be able to get the depth information of the object scene. So for example, here we know that, okay, the flower is slightly closer to us, whereas the tree is further away. So this is how we can perceive the 3D information. It's called stereo opposites. And then based on some calculation, our brain will be able to figure out the depth information. And perhaps some of us will think that, okay, so actually only one eye may be able to perceive the depth as well. And I actually think that it is also true, but I think the main reason on that is that our brain is trained on 3D information with our two eye already. So sometimes if we only have one single eye, and based on our prior knowledge, based on our prior experience, we would be able to still perceive the depth information. But definitely with two different eye, left and right, we will be able to perceive that more accurately. So this is how we get to see the 3D object scenes by our eye. So now let's go back to the camera, 3D imaging camera that we are investigating. So now I'm going to slide number 3. So conventional camera, which have a single aperture, it actually behave as a single eye of our human being. So it has a imaging sensor towards the back end, and then it has a lens in the front. And like more advanced camera, there could be more lens. But whether it is low-end camera which have only a single lens or high-end camera which have many lenses, all of them actually they form a single column, and they align with the imaging sensor, just like our eyes, right? So with only a single aperture, the camera will not be able to perceive the depth information. But on the other hand, if we do want to get the 3D information, what we can do is that we can change the focus of the lens, basically the difference, the distance between the image sensor and lens. We can change the distance, for example, that we will be able to focus on different depths. So this is manually. And then by taking like image at different depths, different focal distance, that we'll be able to get the 3D information. So that is how the conventional camera will be able to get the 3D information. But that will require us to take so many photos, or at least multiple photos, at least 2, right? And another feature of the conventional lens, I will probably not say feature, but one of the disadvantages is that the lenses are usually quite bulky. So imagine that if we have a high-end camera, the lens in the front end is quite heavy actually, and quite bulky, frankly speaking. So I would say that it actually offers a good advantage in the sense that the image quality is extremely good, but on the other hand, it's quite heavy and very bulky. So this is the conventional camera. And then in the past years, there's actually some interesting research. Is called a mask-based camera, or the lensless camera. So by definition, the mask-based or the lensless, it actually means that it replaces the bulky lens, which is usually in 3D, right? You replace this bulky lens with a thin optical mask. And this optical mask is pretty much a 2D plate, a very thin two-dimensional plate. So, and these plates could have like different features. For example, it can be amplitude mask. So basically, it's kind of like this mask. It has many pinholes on the top. It has many pinhole on it. This pinhole can be arranged differently, or it can be a face mask such as a diffuser or a very thin layer of micro lens array. So by replacing this bulky lens with such a thin layer of optical mask, the entire camera can be made very, very thin, right? So, and then on top of that, it can actually perform a 3D imaging in a single shot. So a single shot means that you can just take one single image, and then we can use computational algorithms to refocus so that we will be able to perceive the object scenes at different depths. And we will be able to accurately get the depth information of the object scenes as well. So this is so-called a mask-based or lensless camera. So the main principle of this so-called mask-based and lensless camera is that one single object point, instead of projecting to the camera into a single point, just like the conventional camera or our eye. So for example, our eye actually mapped the object scenes into our retina pixel by pixel. So it's one-to-one correspondent. One pixel or maybe one voxel on the object will map to one pixel on our retina, right? Or one pixel on the camera sensor. That is how the conventional camera works. But in this mask-based or so-called lensless camera, one single object point or one single object voxel will be projected to multiple points on the camera sensor. So, and based on this information, and also some information I will talk later in the following slides, that we will be able to computationally recover the 3D information of the object scene. So this is just like an overview. In the following, I would like to discuss more detail of this lensless camera that we realized in slide number 4. So let's go to the following slide in slide number 4. So what we do is that we implement the optical mask as a thin layer of micro lens array. So we would like to emphasize that although it is a single layer of micro lens array, although it has a lens there, but this lens itself, is very thin. It's essentially a very thin layer. You can imagine that it's just a two-dimensional sheet, very fast sheet. So as a result, we no longer have the bulky lens. So as a result, we can also classify this as the lensless camera. So just want to make the terminology more clear here, right? So now let's take a look at this slide number 4, like panel A there on the top. So what that shows is that a single object source will project its light through this lensless camera, which is composed of that single layer of micro lens array and the camera sensor. And the distance between this micro lens array and the camera sensor can be very small, right? It can be on the order of like a few millimeters to maybe up to tens of millimeters. So it's very thin, yeah. So the entire thing is very thin. So one object point will get projected to the camera sensor, and then on the right hand side you will see that there are many dots there, and that is how a single point will be mapped to the camera sensor. So instead of one-to-one correspondence, it's really one-to-many mapping between the object scene and the camera sensor. And more importantly is that as this object source move in the axial direction, meaning that the distance between the object source and the camera, as that distance change, these patterns on the camera sensor will also change. So, and then we call this pattern is something called PSF. It's called point spread functions. So that's why it's called PSF. So point spread function meaning that how a single point at the object scene is spread onto the camera sensor. So that's why it's called point spread function. So here, the point spread function has many different points on the camera sensor. And importantly is that this point spread function will change when the distance between the object source and the camera sensor distance change. And by leveraging this information, we can computationally recover the 3D information of the object scenes. So in the bottom panels, we show one particular example. So here it has a 3D scene, so it's basically 4 different kits there, and then each kit, the distance between that and the camera sensor is different. And then what happens is that on the camera sensor, we'll be able to capture a single image of the entire scene. And as you see in this image, that is the image right after the camera sensor, we'll see that we can probably still see some feature of the 4 kits as the objects, but more or less it's very difficult to distinguish the detailed feature. the reason is that one single object source is projected to so many different points on the camera sensor. And because you have many different point source on the 3D scenes, right? You have 4 different kits, and each kit have many different washer. So as a result, all this information, they get scrambled and overlapped. So that's why on the camera sensor, we won't be able to see something that can perceive by a normal human beings, right? So and then, but this information is important. Actually, the scramble information is important. It can facilitate us to work out the 3D information, which I will discuss more detail on the algorithm later. But here, we show that after the reconstruction algorithm based on a deep neural network, that is where the two box identify, and then afterwards we will be able to refocus the object seen into different depths. So as we saw on the right hand side, we'll be able to focus on the case that is the most further away, and then the middle one, and finally the one on the front, right? And then for each one, we see that the corresponding case we want to focus will be in the focus position. Its sharp feature is shown, whereas the other information, the other kids either in the foreground or background, they will look blurred, right? So this essentially is like how we use our camera to focus on the different depth, and then we can take multiple image, and each of them focus on different depth. This is how we can recover the same information, but here we just need to take a single image, take a single exposure, and we don't need to change anything on the camera. We don't need to change the zoom or the distance between the lens and the camera sensor, right? So single image through the reconstruction algorithm, we'll be able to recover the information at different depths. And then furthermore, we can further synthesize these informations. And then this is shown on the right-hand side. We'll be able to get the all so-called all in focus imaging. So all the kits here will be focused, and we can also calculate the distance or the depth information of each individual kit here. So this is an overview of the work that we did. So it's 3D imaging camera. So later we will discuss more information about how we design the micro lens array, and also how we do the imaging reconstruction algorithm. But before that, let me show you some imaging experiment results. So this is in slide number 5 of the PDF. And here, uh, in panel A, we actually line up 5 different toys, and we get the permission from the toys creator or the vendor, so that we are allowed to use this for publication here. So we align them in a line so that each toy, they are at a different depth. And then we put our camera in the front, and we take a single image of that, single exposure. And that raw image on the camera sensor is shown on panel B. So here you can see that the same object scenes, they copied into multiple sub-image. So of course it's very small, each one is very small. And more importantly is that each of these copy, they are actually viewed by the camera sensor from a different perspective, because we have many different micro lens units there. So let's say that we have 40 micro lens units, then we will have 40 different sub-image on the camera sensor, and then each sub-image is viewed by the camera from different perspective, just like our 2 eyes, right? We only have 2 eyes, so but we can already see the 3D information. We can get 3D information here, but here we have many different micro lens units, so that we will be able to see the object from different perspective, and based on that, we'll be able to get the 3D information by the calculation. So shown in panel C is that we will be able to refocus onto different toys, right? So the toys are in a line from near to far away, and we will be able to focus at different depths here, from 22 centimeter all the way to 50 to 60 centimeter away. And let's go to slide number 6. And using all the 5 different with focus image that we saw earlier, we'll be able to get a so-called all-in-focus image. So in the panel A here. So actually, I remember we not only synthesize not only we focus on 5 different depths. I think we remember we focus on about 14 different depths. And as a result, we have 14 different image by post-processing, and then we can synthesize them all together. We can get an all-in-focus image. So every feature will be in shot. Will have a very good sharpness, and also we'll be able to get the depth information of different toys here. So this is the all-in-focus image and the 3D imaging experiment. And the other interesting experiment that I would like to show is in slide number 7. So in this particular example, we want to show the capability that the camera will be able to see the object behind some obstacle. So so on panel A, we show we have the camera there on the left. And then on the right-hand side, there will be 3 different objects, actually 4 different objects. The first 2 is on 25 centimeter away. And then there's one at 36 centimeter away, and then another one is 45 centimeter away from the camera. So there are 3 different depths. And then the first 2 objects is partially blocking the 3rd and the 4th object. So meaning that the 2 objects at the first distance, 25 centimeter, is partially blocking the 2 objects at 36 and 45 centimeter away. That is shown in panel B using a cell phone camera. And then now, because our lensless camera, it has a large enough aperture. So as a result, some of the micro lens units is able to kind of image this object scene from the side angle, although it is still partially blocked by the obstacle in the front, but the camera will be able to, some of the micro lens unit will be able to perceive or image the object behind or far behind from the obstacle. And based on those sub-image, which is shown in C and D, that we will be able to refocus on the different depth, and we will be able to clearly see the image after the obstacle, right? To see the object after the obstacle. So that is shown in panel E there. So we can see that the first image is focused on the 25 centimeter depth. That shows the 2 3D printed object. And then after that, we will be able to show focus on 36 centimeter away, which will show the first toy, that is the red color toy. And then after that, we can focus on to the 45 centimeter one, the one further away. So that is how we can do this see-through obstacle. Of course, this is not I mean, this cannot this is just one particular example. If there's something that in the front that is very large size, so that it totally block the object behind that, then we won't be able to see that. And then in that case, we probably need to have a much larger camera in able to see that. So for example, if the camera is wide enough so that part of the micro lens unit at the edge will be able to see the information behind the blockage. So this really depends on how large the obstacle is, right? But nevertheless, this experiment that shows how powerful the 3D imaging capability is, right? So so this is the main experiment that I want to describe. But in the following 2 slides, we would like to go through a little bit more algorithm or a little bit more detail of the micro lens array that we design and manufacture. So now let's go to slide number 8 here. So here, I'm sorry that it could look a little bit dark, but here what we want to show is the PSF of the optical mask. So remember, the PSF is called a point spec function. So the definition of that is that what the pattern is on the camera sensor when there's only a single object source before the camera. So that is point spec function. So here we use a microlens array as the optical mask. So as a result, if we have 40 microlens unit, for example, I believe here we have 37. So then a single object source will be projected to 37 points on the camera sensor. And then the location of each point on the camera sensor is depending on where that microlens unit is. So in our realizations, we design something called a random microlens array, meaning that the central position of each lens unit, they're kind of randomized. So that is how you see in panel A there. You see many different dots, right? So that is a PSF. And these dots looks the position of them is kind of random. So this is how we design the lens units. So A is in measurement and B is our design. So pretty much they are similar. So the advantage of this random microlens array is that it has a very high optical transmission efficiency, and then also for each individual points there on the camera sensor, it is locally confined, and it's also relatively spatially sparse. So this is important as it can reduce the imaging background. So compare with the PSF shown in panel D and E, which is some other work by Professor Laura Wall at UC Berkeley and Professor Jacobs Robertson and Professor Ashok Gangwan from Rice University. So compared to those work, that the microlens arrays PSF is more sparse and is also more locally confined. And we think that this could have some benefit to reduce the image background. So so that is a comparison with panel D and E, which is used in 3D camera called diffuse cam and 3D camera called phase cam. And the image, the panel D and E is showing the PSF of those two cameras, which is quite dense compared to our micro lens array. And then some of us may ask that what is the significance on making the micro lens positions random compared to a periodic one, which is nicely arranged in a grid structure. What is the advantage of that? So so the argument that we want to make here is that in our case, the random PSF it has a low self-correlation, and this could reduce artifacts in the reconstruction. So let me give one specific example here. So in panel C here, we show the periodic structure. I mean, we show the periodic microlens arrays PSF. So there, because the PSF is very periodic, so as a result, it's a little bit more difficult to distinguish two different points. For example, if there's a point source located at one of the grid points of this PSF, and whereas there's another one located on another grid point for this PSF, then the image of these 2 point source will be very similar. Because the PSF is periodic. So as a result, that's their image is just lateral shift, and the lateral shift, if it shift by one period, then it will overlap with the original one, and it's difficult to distinguish whether this source is at A position or B position, for example. So and that is the disadvantage of something called a high self-correlation, right? So if we can do a randomize, then we will be able to distinguish these 2 point source. It will have a less chance to have arbitrary like or some uncertainty on the reconstruction. So we argue that the random position of the microlens unit can reduce the artifact in our reconstruction. And finally, this microlens array's point spread function, because it's locally confined and spatially sparse, so particularly locally confined, very short, and then so it has a wide frequency support, and then in the Fourier domain, and as a result, it has a relatively good spatial resolution. Sorry that this goes into a little bit more technical, but this is how we design our microlens array, and then this microlens array is fabricated through 3D printed. So how it works is that the mold of this microlens array is printed, and then we pour the polymer on top of this mold, and then we let it cure and solidified, and then we can peel off this lens, microlens array, a very thin layer of polymer, and then we just attach to the front of the camera sensor. So this is how we manufacture this microlens array. Okay, and then in slide number 9, in the following slides, that is we show the architecture of the reconstruction algorithm. So after we take the raw image, which have multiple sub-image, actually 37 sub-image, well, they can have overlap as well, partially overlapped, and then we use the deep neural network to do the object reconstructions. So deep neural network is actually a very powerful tool that emerged recently, and then basically it's like it has input layer, and it has processing, many processing layer in the middle, and it has an output layer. And then this deep neural network can, depending on how it is designed, it can do many different things. So very popular example is that if you have an image in as an input, and then the output can tell you what type of image is this. For example, whether this is cat, or it is a dog, or it is a tree, or it is a monkey, it is a rose, it is a flower, for example. So this is one popular example of deep neural network. But there's also some application of deep neural network. And here, what we try to do here is that we put a raw image at the input layer, and then the output layer will be the reconstructed object seen at a specific focal depth. So this is also one application of deep neural network. So here in our particular reconstruction algorithm, we have two different modules. So the first module is something called reconstruction module, and then this is physics aware deep neural network, meaning that we use top-down approach and then we embed some physical intuition or physical information of how this camera works into this deep neural network. So as a result, this deep neural network, at least in this reconstruction module, it can learn the information very quickly, and then it can process very quickly. And then, so after this reconstruction module, we'll be able to recover the object seen at individual depth. And then afterwards, we do an enhancement module to reduce the artifact, so that we can have a reasonably human perceive that reasonable image that we human being can perceive well. So this is what the enhancement module do. So overall, our innovation here is that we design the physics-aware deep neural network as a reconstruction module, so it is easy to train, and then the entire reconstruction can run in a very high speed, actually in real time. And I would also like to point out how the conventional reconstruction algorithm work. So before the neural network, how the conventional image reconstruction algorithm work. So that is work by iterative optimizations approach. So basically, you have measurement, and we also know the PSF. So based on these two information, that we will be able to like fit the object information or to find the object information, so that under this object information, if we use the point spec function, we'll be able to get what is shown on the camera sensor as the measurement. So this is actually called the iterative optimization. It is an inverse problem. Inverse problem means that based on the single measurement and also based on the point spec function, we'll be able to inverse this process so that we find the object. So this is the inverse process using iterative optimizations. But usually this approach is very slow, and also it is kind of something called ill-defined problem, meaning that we'll be able to find multiple solutions as the object that can satisfy the so-called forward model. So as a result, that it's hard to tell, okay, whether this solution or that solution, right? Because both solutions could be correct. Because under this lens, if you use both solution as the object, that's both of them will be able to like lead to the measurement on the camera. So this is kind of an ill-defined problem. So usually, in order to choose the best solution, we will need some prior knowledge. For example, sparsity in the spatial domain, meaning that the image that you recover could be smooth, right? For example, so based on this prior information, that we can recover the object scene. So this is how the conventional work algorithm work. We have two disadvantages. Number one is that it's very slow. Number two is that it requires prior information, and this prior information is kind of empirical as well. So this is the disadvantage for the conventional image, but for the conventional algorithm. But here we use the deep neural network, which is very fast, um, and it's relatively straightforward as well, because we inject the physical information there, so that we will be able to recover the 3D object scenes in real time. And one important thing I want to point out here is that if in order to do the training, we actually do not need to know the point spec functions. So how we train is that we set up a monitor in front of the 3D camera, and then we display different image on the monitor as the object scenes, and then we will be able to capture this image using the 3D camera we have, and then so from there we have a pair. So we have the ground truth object, which is displayed on the monitor, and we have the measurement. And by using this pair of information, and of course we have multiple pair, then we will like be able to train this neural network, deep neural network, and then this new deep neural network will be able to figure out the reconstructions logic and reconstruction algorithm. And later, if we present a new object, right, for example, that we will be able to recover this object. And then another subtle detail is that during this training, we also move the monitor to different position, different depth, so that the neural network will be able to learn the depth information as well. So this is how the reconstruction algorithms work, basically using a deep neural network to do the reconstruction. And then now we finally come to the slide number 10, so which is a summary of what we have so far. So basically, we saw that with using a custom micro lens array, we'll be able to make a very thin and compact 3D camera. And then using this camera, we can take a raw single measurement of the object scene, and then we'll be able to recover the 3D information through a physics-aware learnable network without any measurement of the point spread functions, unlike the other iterative optimization approach or some other deep neural network. So here we don't need any information of the point spread function. And also I set up a reference here of the paper. Now, in the final few minutes, I would also like to go back to what I discussed earlier about the biomedical applications. Before this project, we also made another camera. So this camera is I would say that it is smaller, but the principle is very similar, though the reconstruction algorithm is different. Let me briefly describe. So at slide 11, at panel B there, you will see the 3D microscope, lensless microscope. Basically, is a camera chip. In front of that, there is a micro lens array as well. Of course, the design is a little bit different from the photography application that we showed earlier. And then again, using our reconstruction algorithm, which is slightly different from the deep neural network. So here we use the geometrical optic to actually back project the measurement back into the object domain, and we use some background suppression algorithm to further process the reconstruction. So as you see in panel C, we'll be able to find out the information at different depths, and after that we use background suppression algorithm, which can also be a deep neural network, so that we can remove the background information, and then we can get the sharp feature at different depths, even though this feature could overlap with those at other depths, right? So this is at slide number 11, and slide number 12 is one specific imaging example here. So in this particular example, we create artificial object using phosphorescent objects. So that is shown in panel D, and then we image this through the lensless microscope, and then the raw image is at panel A, right? And then after our algorithm will recover the different depth feature at panel B, and then we further remove the background, and then that is panel C. So here you can see that from 20 millimeter to 25 millimeter, so only within 5 millimeter depth, we'll be able to find the feature at different depths. So here it is basically a snowflake, and then this snowflake is tilted so that we will be able to get some of its feature at different depths. And using all this information, we can recover the full 3D tilted snowflake that is shown in panel D. Panel E there. Different color there means different distance. Okay. So this is the 3D microscopy applications using the lensless imaging. So finally, at slide number 13, I would like to acknowledge the work of my students. So without my students' hard work, which is mainly my PhD student Feng Tian and other group members in our lab, we won't be able to achieve the good result of both projects. So, and I would also like to acknowledge the funding source, particularly the funding source that for the second second project here is the biomedical application one. That's slide number 11 and slide number 12, right? So that is from National Institute of Health and Burroughs Wellcome Fund. And then for the photography applications, and then we also acknowledge the funding from UC Davis for my startup package. And finally, I show the two reference paper there, which can further describe the two work that I described today. So this is pretty much what I want to say, and sorry that took a little bit longer than I expected, and maybe sometime I repeat myself too much, and sorry about that. But thank you much. Yeah.
No, thank you so much for giving this wonderful talk, and it's so impressive, this technology that you developed, and it's so useful also. So yeah, thank you for explaining it to us, and
Thank you. Yeah.
yeah, it was really wonderful. And everyone, please ask your questions, post them in the chat, or come to the stage. And let's just go in PTR order. Serena, do you have a question? Thank you.
Sure. So that's a really interesting talk. I'm first curious about the details of what you can tell me in terms of the microlens layer. Is it
Mhm.
in terms of the the suggestions of the cover the photonics? Is it actually a variety of curvatures laid out on an
Ah,
area?
yes, yes. So in this particular case, so we can imagine that each microlens unit is like a small dome. And then it's sitting on a thin substrate. But each of these dome can be very small. So it can vary from uh, uh, like 50 micron to 100 micron. So 100 micron means zero point 0.1 millimeter to 1 to 2 millimeter or a few millimeter height. It depends on the application here. So, and then we'll arrange many different domes, okay, on top of the substrate, and that is how this microlens array layer is manufactured, or and there's also some other technology, as I mentioned earlier, that is pure 2D. So, for example, in the diffusing cam, uh, like camera that I compare earlier, there um, a single layer of diffuser is used. So there is really two-dimensional plate. It has some thickness, of course, but thickness is very thin. And then you can imagine that is like a diffuse uh, glass, right? So diffuse glass, so that can be totally 2D. Or there's also some other optical mask that have uh, like it's basically made from a transparent glass, but they deposit some kind of black uh, like coverage on some of the area, so that some of them is exposed as the transparent glass, but some of the area is blocked. And then that blocking layer can be extremely thin as well. So there, that it can also be a totally 2D structure. Yeah, but for us, I would say that is also kind of 2D, but some of the dooms there protrude a little bit out, so it's a little bit more like a 3D. Yeah, but it's very thin overall. Yeah. Mm-hmm.
Really interesting. And so I have another kind of bizarre question is I'm
Mm-hmm.
wondering there'd be distinct advantages to having this, as you pointed out in the beginning, of having just a thin layer without, being
Yes.
a lens.
Yes.
I'm
Yes.
wondering, it's just kind of a curious thing.
Yeah.
I'm curious, why not? Are there examples that where such a system was evolved biologically for those similar advantages? And it's
Uh-huh.
kind of
Uh-huh.
it's kind of a curious thing if they had.
Yeah. Yeah, so I would say that biologically there is indeed something like this, particularly for the microlens way. So this is the compound eye by the
Mhm,
insect. So a lot of insect they have the compound eye, but
right.
the detail structure is a little bit different. So basically each small eye there's not so many pixel below that. So I believe each eye, so it depends on the nature of the insects or different creature. So some of them only have one pixel, and some of them have a few pixel for each eye. And then they arrange in 3D. So the main advantage there is that they have a really large angular field of view. So that means that some insect they will see something behind that, because the micro lens array or their compound eyes is it's arranged in a sphere, and also with this structure, they will be able to perceive the 3D world better, I would say. So this is somewhat similar, but not in the sense of a thin or compact camera. So yeah, so this is something different. And I would say that one application of this thin structure is for endoscopic application. So it can, so the device can be thinner. And another key advantage is that it can do a large field of view imaging. So for conventional camera, if we want to have larger field of view, we basically want to make the lens bigger, make the camera sensor bigger, right? So it not only extend in the natural XY dimension, but also in the depth dimension as well. So, but this lens, so-called lensless imaging devices or the mask-based devices will overcome the challenge that um, in the sense that we can extend the light field of view by just making this optical mask bigger in the XY dimension, but you don't need to increase the thickness. So as a result, the entire
Right.
camera can still be very thin. Yeah. So that is
Mhm.
the advantage. Yeah. Yeah.
So one last question: Are
Mm.
there inherent limitations to this approach
Mm.
for larger distances, for farther out?
Yes. Yes. So for larger distance, that's a very great question. For larger distance, actually, we won't be able to perceive the 3D information because the angular um,
Mm-hmm.
information is lacking. Because if the object is too far away, that maybe 100 meter and 101 meter, pretty much they look the same distance. And in order to have do the 3D information for those, that we will probably have another camera that is separate a little bit in the XY
Sure.
location. So
Mm-hmm.
just like our eyes, that the left and right they separate a little bit more. Yeah. So as a result, for this is more for the like close distance. Yeah. Hmm.
Mm-hmm. Well,
Hmm.
thank you.
Yeah.
Fascinating.
Thank you. Yeah. Mhm. Thank you.
Frank, do
Hmm.
you want to go ahead and ask a question?
Yeah, yeah. Thank you, Katerina. Thank you, Wenjian, for sharing with us this interesting research of yours. And learned a lot from the previous conversation with Serena. I also, thought of the interesting, the biology evolution that offered us the amazing, compound eye, as you mentioned, of the insects, and
Hmm.
seemingly that the micro lenses are as you explained, that there's the pixel, the resolution is of yours is higher,
Yeah.
and similar problem with the distance,
Hmm.
far field, middle field versus near field. So
Right.
I would gather right now you're focusing on mid and near
That's right.
range, right?
Yes.
Okay.
Yes. Yes.
So I would thanks for the organizers, the very careful sharing the information. I actually found a paper of
Mm.
yours. So in the appendix, the A, the you actually answer provide answers, but I didn't get understand on the fly the number of lenses that you calculated.
Mm.
It seems to be 37,
Yeah.
and could you seemingly the aperture is also a parameters. I didn't see it somewhere, but
Mm.
I'm a miss. Yeah.
Yeah, I think the aperture here is actually quite large. The entire aperture, if I remember correctly, it's probably 15 millimeter. But I don't have the exact number on top of my head, but it's on that range. Um, so 15 millimeter diameter in total. And then within this 15 millimeter diameter, we have about 37 lenses. Yeah. So how we design this is basically is really based on our application. So obviously, if each individual lenses is bigger, then we probably cannot make 37. So maybe we can make maybe 4 to 5, for example. And then from there, that the advantage there is that the spatial resolutions could be improved in the XY and also Z as well. But the disadvantage there is that the depth of focus, meaning that the range that we'll be able to see will be smaller. For example, maybe that could only see distance from 10 to maybe 25 centimeter on that range. But here, by making each individual lens smaller, that we will be able to extend this from 10 to 50 to 60 centimeters. So we have a larger depth of range. But of course, the disadvantage of this have more lens compared with fewer lenses, that the XY resolution will be degraded compared to that. So by the end, it really, I think it depends on the application here. And in our application here, I believe that the resolution can go down to about like millimeter scale. So which is maybe enough for some of the photography for a 3D detection application. But on the other hand, if we want to have a higher resolution, or maybe we want to, instead of just from 10 to 60 millimeter range, 10 to 60 centimeter range, we want to see a little bit more further away and everything simultaneously, that we can adjust the size of the individual lens units and correspondingly change the number of the micro lens units. So this is how we decide. Yeah. Mhm.
Thank you.
Yeah. Thank you for the question. Yeah. Mhm.
Thank you. Hey, Eli, do you want to ask something or say something?
Well, so unfortunately, I wasn't able to pay attention through the whole thing, but it did cross my mind that so I would probably have better questions, and I do look forward to listening to the replay for those sections. But I was wondering if there would be any sophisticated applications to using this in combination with media that can do holographic recording to
Mm.
get any better results than you would conventionally.
Yes, certainly. So I think with these applications, I mean, with this device, we'll be able to capture the 3D media, so that we will be able to store, I mean, with some other development, that we'll be able to store all this information frame by frame. And then later, maybe using some other devices that we can display this back, right? So this will be a good like application to store the 3D information. So of course, holographic recording is it's a technique that can be used to do the recording. But here, I think using our camera, the setup will be less sophisticated, and then compared to holography, and so that is of course one application. And another application I would say is more for biomedical application that I mentioned earlier in the talk, and also towards the end of this talk, that we were able to make the entire like camera extremely thin and extremely small and light, so that we can put it on top of the animal's head, and then we can record the brain activity, for example, while the animal is freely behave. So we are currently working towards this end goal at this point. Yeah. So and actually another sorry, not another. So the Frank earlier asked what is the size of the aperture. So I replied 15 millimeter in diameter. That's actually not correct. It's actually about 24 by 36 millimeter aperture. So it is arranged in a rectangular shape. I mean, that is the camera sensor shape. So that is also the area of the microlens unit that can be used. So it's 24 by 36 millimeter, and each lens unit has a 3 millimeter diameter. Yeah. Mhm. Thank you.
And
Yeah.
so would further miniaturization as well as larger overall um, uh, uh, surface areas together, improve resolution or depth of field?
Yeah, certainly. Yeah. Yeah. I would say that if we have a larger sensor and also a larger array. That means that we have more microlens unit there. We will be able to see a larger field of view. But on the other hand, for the resolutions and also the depth of field, that is more related to the individual lens unit. So if we can make the individual lens unit bigger, that will improve the resolution but sacrifice the depth of focus. So the main rationale to increase the overall area of this microlens array, meaning we giving the same size of microlens unit, we fit more microlens unit on the entire way, is mainly to increase the natural field of view. So instead of just imaging a 1 centimeter by 1 centimeter area, we'll be able to image maybe 5 by 5 centimeter area if we have like more microlens unit, and also assuming that the image sensor can be bigger. Yeah. Mhm.
So over the years, I've run across numerous papers on fabricating microlens arrays, and I recall that various methods perform differently in terms of the exact contours of the lens. So for instance, if methods that depend on differences in surface wettability, with the surface then being covered by or exposed to a polymer solution, and it only retains it in the wettable areas, and then the polymer is cured in whatever way
Mm.
that can lead to certain deviations from perfect spherical geometry, etc. I'm wondering firstly, how sensitive is what
Yeah.
you're doing to such issues,
Mhm.
and what, if this isn't like a trade secret detail or anything,
Oh, yeah.
what methods do you think are most
Yeah.
promising?
Yeah, so this is definitely not a trade secret. So what we do is that we actually outsource these designs to a 3D printed company. So this company has very special technique that can print the small feature while overall with a very smooth contour. But we are not printing the lens directly because mainly because of the material is not suitable for us. So what we do is that we have the company to print the mold for us. And then and because this is 3D printed, so the contour, exact contour can be very flexible. So that can be designed by us actually. And then we send the design to the company, and then they print out the mold for us. And this mold, of course, depending on the exact technology that they use, it may have some deviation from the design, but I would say that overall it is quite smooth. Uh, and then what we do after is that we pour the polymer on top of this mold, and then we let the polymer cure. So as long as the mold is accurate, then these when we do the casting, then we pour the polymer onto this mold, and then we let it cure, and then we lift it up. Then the contour of this lens will be accurate. So by the end, it depends on how accurate the mold is. Yeah. So, but overall, I think this techniques, it has the advantage of being very flexible, very flexible. And then there's also some other techniques using diamond turning, for example. That's more conventional, but it's much more expensive as well. And also there's some other techniques using the nanofabrication technique, they use the photoresist, for example, first do the patterning and then do thermal reflow so that each rectangle block can become a sphere or something like that. But the disadvantage there is that, number one, the material that they can use is limited to the photoresist. And number two is that it's really hard to control the contour of each individual lens unit. Whereas doing 3D printing is more flexible, I would say, because it's all designed by us, and then we can decide whatever shape that we like, as long as the printing is accurate enough or precise enough that we'll be able to achieve what we want to have. Yeah. So this is what I think. Yeah. Mm-hmm.
So one of the areas that I work in are or is improving certain aspects of roll-to-roll manufacturing, down to submicron geometries. So maybe we can discuss this in further detail in the
Mm-hmm.
future, because this is to kind of take roll-to-roll patterning to the next level.
I see. Sure. Yeah, I would definitely love to discuss some more with you later. Yeah, perhaps. Yeah. Mm-hmm. Yeah, and you can always find my email on the paper that's about this project, and then we can communicate through there as well. Mm-hmm. Yeah.
Yeah, thank you so much. Abyss, did you have a question? Please go ahead.
Thanks, Scott. Hi, everyone. And thank you, Wenjin. This is really fascinating work. I'm always curious about to hear what the next breakthrough is when it comes to optics.
Mm-hmm.
And it seems like, I mean, this has a lot of promise, especially in my field, where you're basically equipped with like a stereoscopic endoscope into into a patient to essentially look at without to have like a very minimally invasive surgery. So I think like this will have tremendous implications in that regard. So based on um, based on what you presented, I had a few questions for you. So the first
Mm-hmm.
one is that how do you actually guarantee that the sort of the random micro lens array actually doesn't have sort of a self correction in a way, pretty much like what the periodic approach does.
Mm.
So do you actually correct for or look for some kind of, say, like a two-dimensional Gaussian distribution so that you don't have potential overlap?
Uh-huh.
Or and if you do so, how do you correct for, or at least like how do you account for possible um, images that cannot be resolved if
Right.
that's an issue?
Yeah. So thank you for this question. So actually, for this particular work, we actually do not specifically optimize the position of the microlens weight. I mean the individual microlens units. We just kind of set it random. So random meaning that there are some certain bounds of the minimum distance and maximum distance between the two lens units. So as long as it's within that bound, that we are fine. And overall, because it's kind of like a random process, so and it's quite different from the periodic cases. So I believe that the so-called self correlation it's very low here. But I would also like to point out that there's also some other design philosophy that can actually do end-to-end optimization, meaning that based on quantity that we have and based on the reconstruction algorithms, we can also update the design of the lens units so that the entire hardware and software is looped together. So this is a joint optimization of the hardware and uh, software, which we have a project earlier using this principle, but it's very different from this one. So I believe that if we use that, that can further enhance the quality. But in this particular work, I would say that for the micro lens await, we kind of use our own empirical experience to design that. So and as a result, we didn't put that into the end-to-end optimization fashion. So the neural network is only for the reconstruction. But if we include that in the neural network optimization, that certainly, I believe that the performance can be further enhanced. Yeah.
Gotcha. Yeah, I see. That actually kind of makes sense. I'm also curious, have you tested it on different types of light source? Like, for example, if the diffuse light actually kind of skews your prediction to predict the depth
Ah, yeah,
information more
yeah,
than the main source.
certainly, yeah. So for this particular work, we use the warm lights to do the illuminations, and sometimes we can enhance the lighting by a white LED, but basically they are kind of diffuse lights. Um, and then in the biological application side, we use both fluorescent and phosphorescent. So meaning that each point source is actually emit light by itself. It emits a full 360, a full 4 pi solid angle. So that is how how we use the lightning condition. Basically, is totally diffuse light. And on the other hand, can we use some more collimated light? I think it will probably work as well, because when the light shine on the object, it will diffuse to different direction, and then we'll be able to connect that. And then that's basically how the PSF is recorded. It's basically a point source that emit light at all the angle, and then we can capture that on our camera. So that's how the PSF works. So as a result, that I think the lighting condition here may not be so critical, but here we use a diffuse light or have the object to emit light by itself. Yeah.
So I see. So polarization is not an issue.
Yeah, polarization is not an issue at all, right?
Gotcha. So so based on the schematics that you showed in slide 9, that you actually break down the image that you're getting into our red, green, blue, I think, and you're applying FFT to do the reconstruction
Yes.
module. And then I think like you're doing inverse FFT to actually get the sort of like a sharper image. So I'm curious, have you considered using diffusion models, because they seem to be doing much better at denoising such an input data?
Right. Yeah. So that's a good question. So we haven't explored that. Um, we will certainly want to try that as well. So here, the reason that we use FFT here is that it's kind of very fast approach, and we use the deep neural network to learn the kernel of that of the middle layer during the FFT and inverse FFT process, and then that is learned so that we will be able to correct something that cannot be modeled like precisely using top-down approach, and then afterwards that we use an enhancement model to suppress the noise further and then make some more correction. So yeah, so that is how this reconstruction module using FFT and how the enhancement module using UNAC work. Yeah, but certainly we will also like to try other process as well, like the diffusion model could be one of them, and then we can certainly look into that. Yeah, but thank you very much for this suggestion. Yeah.
Yeah, that actually makes sense, since you're kind of analyzing multiple images, and the sort of the fidelity of resolving 3D images depends on how many micro lenses they could have. The more micro lenses, the better resolution. So I think the faster approach can seems reasonable. So I can see why that is, why you're kind of focusing on simple FFT as opposed to using more complex model like diffusion model.
Right.
Last thing, last thing I know is there's one person who joined, who's actually on the stage. My last question is that, have you looked into metamaterials to actually do better resolution for much closer objects? Or is that something that you have on your target as a potential research
Big,
area?
lens away. So there is more flat. So the feature size there is on the order of 100 nanometer. So it's really like a 2D like device. So that is the meta lens array that we are working on. And I think the advantage of that is it can create something that cannot have using conventional lens units. But also there's a lot of design challenge there, particularly for the chromatic operation. So meaning that you can image well for the maybe red color, but for the blue color or the green color, that we need some more correction. So that is there's some complication. Then also some of those design could be polarization dependent as well. But certainly the meta surface or the meta lens or meta structure actually open up quite further enhance the image quality, including the image resolution that you mentioned. Yeah, certainly.
Yeah. Thank
Yes.
you for answering my
Yeah.
questions. I'll pass the mic to the next person.
Thank you very much.
Hey, John. Yeah, go ahead. Thank you.
Thank you. Yeah. I have a question. See, when you use this your 3D camera to take a picture, normally, see how long does it take the computer to analyze those pictures and form a 3D picture?
Yeah. So here, in this particular project, is about 40 to 50 milliseconds per depth. So so it depends on how many depths that we have. So let's say that if we do like 4 different depths, so it will be less than 200 milliseconds in total, and that will become 5 volumes per second. So yeah, so certainly using a higher like more advanced GPU will make it faster. Yeah, but here including everything, all the different color, RGB color, it's about 40 to 50 milliseconds per depth. Yeah.
Wow, that's pretty good. So, so is there any requirement to see for the how long your camera has to be like away from the object?
Yeah. So yeah.
See,
So here in our application here, it's about 10 centimeter away, at least. Um, and then the how far away, it can actually be very far away, but I would say that if we want to do a good job in distinguish the depth, that in our experiment we demonstrate up to about 50 to 60 centimeter away, and beyond that the capability to resolve the depth is weaker, so meaning that we may not distinguish like 2 meter and 2.1 meter, but we will be able to distinguish like 10 centimeter and 12 centimeter. Yeah, so this is more for the close or near object distant application. Yeah.
so do you have to use very strong light to shine on this object
Yeah, so
in order
here
to
we use the
achieve this?
room light. Yeah, we use room light or the YLED to shine light onto the object, so that this object will reflect the lights, and then it will go to the camera. Yeah.
Okay,
Yeah.
thank you,
Yeah.
thank you
Thank
very
you. Yeah.
much.
Yeah, thank you very much for all the questions. And we've been going on for an hour and a half. So thank you so much for sharing all this time with us and this knowledge and answering all of our
Well, of
questions.
course. Yeah. Thank you very much. Yeah.
Thank
Thank
you.
you for all your
And
time, actually, and attention. Yeah.
Yeah.
Mhm. Yeah.
The question I had, did you already implant it in animals, and did you have like first
Yeah, we
results
are working on
with
that
having it
now.
in
Yeah.
vivo?
Yeah, we are working on that now, actually on the implantation side. But we haven't got a chance to do the like real imaging on the animal yet. So we are working on the detail on the surgical planning. Yeah, but hopefully soon. Yes.
Yeah.
Yeah. Mm.
Oh, I will be looking forward to learn about it. Maybe someday next year around this time you can come back and
Sure. Yeah.
tell us more,
Hopefully.
maybe.
Hopefully. Yeah. 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 But yeah, it
Thank
will
you
be
so
always
much.
difficult, more difficult on the biological side, because it also depends on the animal and much more work compared to the toys here. For the toys here, we can purchase a toy and get the permission from the vendor to use. But for the animal, it's um, it also depend on the like fluorescent expression, and there's more. But hopefully we can get it done soon. Yeah, thank you.
Oh, and how much would, let's say you would make a company to sell this to labs, like how much would the camera like this cost more or less? Would you know? More or less?
It won't cost too much. Because the only thing that costs is cost a lot of money. Actually, not a lot either. It's a 3D printing mold. So once that is done, then the casting process can be fast, I would say. And the material is very cheap. It's polymer based and CMOS camera. So that CMOS camera can be something that is used on the cell phone as well, which I believe can be very cheap, I think. Yeah. Mhm.
Oh wow, that will be
Yeah.
amazing because usually it's quite everything is
Right.
always so expensive.
Right. Yeah. Yeah.
So yeah, I hope you have great success and maybe you'll sell these cameras or somebody sells it for
Yeah.
you
Sure. Yeah.
for a
Yeah.
lot.
We are always
Be
happy to
amazing.
share as well. Yeah. Yeah.
Wonderful.
Yeah.
Okay,
Yeah.
that's a great last talk because it gives us a good outlook for the future,
Thank you. Yeah.
a positive outlook for the future, and happy holidays to
Mhm.
you and to everyone, and thank you everyone for coming and enjoy the holidays, everyone. And yeah, hopefully I hear you all back in the next year. Yeah,
Okay. Great.
enjoy and thank you so much again.
Thank you again for your time and attention, and happy holiday and good morning, good evening. Thank you.
Thank you
Thank
very
you.
much.
Thank you.
Thank you. Bye bye.
Bye everyone. I'll close the room in 3, 2, 1. Bye everyone. Happy
Bye
holidays.
bye.
Thanks. Happy holiday.